Hello there, TAs for ATS 114. I'm here to talk to you today a little bit about Lab 7, the cloud physics or cloud droplets and raindrops, I believe is what the lab is called here. And we're only doing the first 17 questions of this lab. The second part of the lab is related to an activity that we don't do in the textbook until the very end of the semester, so it doesn't make a lot of sense to do that right now. Now, part of this beginning of this lab here is a little technical detail that you may or may not remember from when you took ATS 114. Remember, we have these graphs of the so-called Clausius-Clapeyron equation, which were previously used in the class as a way of figuring out what we were going to use for the saturation vapor pressure. So, like, remember in the past, we would say, like, if this is the temperature, then this was our saturation vapor pressure. Well, another interpretation of that kind of diagram is to say that any place on that diagram corresponds to, like, an air parcel with that temperature and that vapor pressure. So, like, if I was talking about that spot right there that I just made in green, that would be corresponding to an air parcel that had a temperature of, let's say, 35 degrees and a vapor pressure of, let's say, 11 millibars. So if you had an air parcel with a temperature of 35 degrees Celsius and a vapor pressure of 11 millibars, that little spot there corresponds to that parcel. And, you could take any other spot on the diagram and talk about it as well. Now, the reason why that's a useful way is then places that are above the curve correspond to situations where the atmosphere is actually supersaturated and the relative humidity is greater than 100%, at least for a short period of time. And any place that's below the curve corresponds to an air parcel that is subsaturated. Any liquid water droplets that are in the air parcel will be evaporating. So this is actually a useful way to think about it. Now, what this graph of the Clausius-Clapeyron here fails to illuminate, though, is that actually, as you'll see in the video I made for the students as well, down below 0 degrees Celsius, the curve actually kind of splits into two curves, which is what they're showing down here at the this diagram at the bottom of the page here. The curve actually splits into two curves. One is the saturation with respect to water, and another is when it's respect to ice. It turns out that there is a slight difference in the form of the Clausius-Clapeyron equation that you use depending on whether it was water vapor condensing onto a supercooled water droplet or water vapor that is depositing onto an ice crystal. The two curves are, as you can tell, are practically right on top of each other. But there is a little gap in between them, like where this little asterisk is here. And that little asterisk there indicates an air parcel who is slightly below the curve for liquid water, like supercooled water droplets, and slightly above the curve for saturation with respect to ice. Now, what that means is that if you had a little droplet in a cloud or whatever that is at a temperature down here a little below freezing, like negative 15 degrees Celsius or something like that, if it is in this right little range of vapor pressures here, it's actually slightly subsaturated if it's liquid water. If that's a little liquid water droplet, the relative humidity around it works out to something like, you'll do the example over here in example 1, but it works out to like 98% or something. It's high, but it's not quite 100%. It is subsaturated. That liquid water droplet is going to be evaporating. On the other hand, if that's an ice crystal under the same temperature, the same vapor pressure, if this little asterisk refers to an ice crystal, well, you do it's slightly above the curve with respect to ice. And when you compute its relative humidity around the air around the ice crystal, you'll find it's a little more than 100%, like 102% or something. It's not all that supersaturated, but it's a little supersaturated. So that ice crystal will grow as more water vapor deposits onto it. That's what they're going for here in problem 1. Now, problem 1 actually refers to this graph here that I've been drawing all over here, but it actually gives you the numbers in here. For an air parcel whose temperature is negative 15 and its vapor pressure is this, it doesn't expect you to actually read off of the diagram the saturation vapor pressure. It gives it to you in the problem. And so you'll actually take like 1.72 divided by 1.91 millibars, because that's the definition of relative humidity, right? Vapor pressure divided by saturation vapor pressure, and you should get a number that's a little less than 100. Then it'll ask you the same sort of thing, but it'll ask if it's with respect to ice. That's actually in problem 3 here. So for ice, so you have the same vapor pressure, what was it, 172 or something like that, 1.72, but now it's divided by the saturation vapor pressure with respect to ice. And again, the problem actually gives it to you right there, 1.65, and you'll get a relative humidity. These numbers are slightly faked here, the way they did this here. You'll get something like 110%. So this is actually supersaturated. The ice crystals will grow, the supercool water droplets will be shrinking. In that little area of air right around the supercool water droplet, the relative humidity is a little less than 100%, so the water vapor evaporates off of the supercool water droplet. Whereas around the ice crystal, that air just right around the little ice crystal in the cloud is supersaturated, and water vapor will condense on. That's what they're going for here. That's what's known as the Bergeron process. That's a term that I actually use in the student video there. I don't remember if they actually talk about that in the lab itself, as that being the term here. Then we talk about the forces acting on the droplet, and most of these problems are actually not very difficult at all. Basically, it's asking you to do things like determine the volume of an ordinary cloud droplet. So there's the information it gives you as to like the equation for the volume, and here it is, it gives you the radius. You do the same thing for like a large raindrop. It has you do the same sort of thing for what is the cross-sectional area of the big raindrop. This is its cross-sectional area here, and so on. Now, what this leads to here is this rather difficult question 9. Here in the difficult question 9, it says, since gravitational force is proportional to the mass or the volume of a raindrop, and frictional force is proportional to the cross-sectional area of the droplet, which of the two forces increases more for a given increase in droplet radius? So the mass of the droplet is proportional to the cube of the radius, whereas cross-sectional area is proportional, which is what is related to the terminal velocity of the droplet, is related to the square. The problem is not wanting them to overthink this too much and just basically say, oh, I see, the mass increases as the cube of radius, whereas the cross-sectional area increases as a square. So as mass increases, the droplet gets, as the radius increases, the droplet gets heavier and falls faster. It's important not to overthink that, though, because that's not exactly how terminal velocity works. That's actually, but at the level of ATS 114, that's not a terrible answer. Now, then it does actually get into a little bit about terminal velocity. Terminal velocity being how fast an object can fall through the air. And it gives us some typical values for a radius of a droplet. What is its rate of fall in meters per second? And notice that these tiny little droplets, let me circle some of these numbers here. Ordinary cloud droplets have terminal velocities on the order of millimeters per second. These things, when you look at a cloud is falling. It's just falling at a rate of a few millimeters per second. It's never going to fall all the way to the ground. You need to be a big old fat raindrop if you're going to fall at a fast enough terminal velocity to fall out the bottom of the cloud and actually make it to the ground before you evaporate, which is a totally cool thing. Cloud physics is like a really cool discipline, and the book tries to give a sense of that by like talking in terms of like, okay, here's how far through the subcloud layer droplets of different sizes are going to be able to fall before they evaporate. So like here's all these distances here. I didn't see those meters. I think they are. So like for example, if your droplet's radius is this many microns, which is like 2 millimeters, is that right? It can fall pretty far before it would evaporate. Whereas these tiny little things can barely fall at all before they would evaporate, and so on. And you use that information to like kind of come up with this sense of like how far droplets can fall before. Why do droplets have to be big before they can fall and actually reach the ground? Because they fall fast and they're big. They're hard to evaporate. Okay, that's really all that it's going for there. It just doesn't. It does it in the course of a whole bunch of different little questions that are basically just reading a graph and so on. Same like this graph up here. This is trying to show for different thicknesses of clouds what are the probability the precipitation is drizzle or is rain, depending on whether it is a high cloud or a low cloud. So like, for example, if you have a 3 kilometer thick cloud, I'll draw a line in right there, then a low cloud has a high probability that precipitation is going to be drizzle and a relatively low probability that the precipitation is going to be rain. On the other hand, a higher cloud of the same thickness has a fairly low probability that the precipitation can be drizzle, because if it's drizzling, those droplets can't fall that far, right? They can't fall all the way from a higher base of clouds. Whereas it's much more likely that if it is precipitating, the type of precipitation is going to be rain. That's what they're going for here, just reading this little diagram here. It's not meant to be some super challenging thing. And when you get down, answer question 17, but then that will be the end of it. This other stuff here on this lab activity is actually really cool stuff about the differences between snow and rain and freezing rain and sleet. And I intend to come back to that once we've all done the winter weather module, but that's not till like December, and we may actually not have enough we may actually run out of time. Okay, that's all I needed from you guys. Hopefully that'll help you guys get ready for the Lab 7. Please let me know if you have any questions. This is Dr. John Schrage.